Okay, this is going to be the fifth video on how to find the interval of convergence of a power series, and we'll look at this example this time. And just a reminder, when you try to find the interval of convergence, for some values of x, the series will converge. For other values of x, the series will diverge. And you're going to use the ratio test to determine what values of x works for convergence and also to make it diverge. So just like we've done in the previous videos, let's quickly take a look at the ratio test just to remind you of what that's like. Okay, and what the ratio test says is this, it says if you have a series and the series has non-zero terms, then if you find this limit and it's less than 1, then the series converges. If you find the limit and it's greater than 1, the series diverges. And then finally, if you find the limit and it's equal to 1, then the ratio test fails and you have to use some other test. Now, primarily, we're going to be concerned with this first one up here. We want to know where it converges. So we're going to find the limit, check it to see if it's less than 1, and then we'll know in what range it converges. So that's just like we've done in the previous videos. Now, again, if it's been a while since you've used the ratio test, I would suggest that you back up and watch the ratio test videos before you start on this. So let's go back to our original problem here. And what we've got is this. We've got a series. Now, first of all, just to note, it starts at it says x minus 5, and remember these are always in the form x minus c. So since this is an x minus 5, you know that this particular series is going to be centered at x is equal to 5. So that's going to be the center of the interval of convergence. So let's look, and we're going to use the same rules that we've done in the previous videos. So again, we will use the ratio test to find this limit. And when you find this limit, again, there's only 3 possible outcomes. Either the limit's equal to 0, the limit's equal to infinity, or the limit's equal to a fixed number. And in the first video, we found the limit was equal to 0, which means that the radius of convergence was infinity, and the series converged for all x. The next video, we found the limit was equal to infinity, and the radius of convergence is 0, and the series only converged at the single point x is equal to c. And in the last couple of videos, we found the limit and it was a fixed number, which means that you have a fixed interval of convergence at some distance r, and we found out exactly where it converged in that interval. So we'll do the same process. So again, if you watched the previous video, you'll be pretty familiar with this. And what the ratio test says is this, first of all, in the denominator, you use the original series. In the numerator, you use the original series with each one of the n's replaced with an n plus 1. So I'm going to go ahead and first of all just write down the original series in the denominator. So what that would look like, I would have a negative 1 to the n power. Then I've got x minus 5 to the n power. And that's all divided by n times 7 to the n power. Now in the numerator, write the same thing down, but everywhere you've got an n, replace it with an n plus 1. So this is going to be, in the numerator, I would have minus 1, only this time it'll be to the n plus 1 power. I'll have x minus 5, again to the n plus 1 power, then all divided by, this will be, in place of n, I'll put an n plus 1, I think I'll put in parentheses. Then I'll have 7 raised to the n parentheses n plus 1 power. So it'll look like that. Okay, now it's just a matter of simplifying this, so we'll bring it up to here. Now this is something we talked about in the last video. Sometimes this minus 1, you've got a minus 1 to the n, you've got a minus 1 to the n plus 1 power. And in the previous video, we discussed that all this can be, it is either a positive 1 or a negative 1. So both of these two terms can only be a positive 1 or a negative 1. But when you wind up taking the absolute value of it here, it'll always turn into a positive 1. So both of these terms will always only be a positive 1, and since when you multiply 1 by anything, it doesn't change anything, basically you can forget about these two. So that part's pretty easy. You can eliminate them because, again, the absolute value of negative 1 is 1, the absolute value of 1 is 1, so for all practical purposes, those two terms disappear in this problem. And if you take that as a first step, that'll make things a little bit easier as we go through the rest of it. So now we'll do just what we've done in the other videos. We'll make this be the limit as n goes to infinity of the absolute value And again, we'll change it from a division problem into a multiplication problem. First of all, we'll write down the numerator, and that's going to be x minus 5 raised to the n plus 1 power divided by n plus 1 times 7 to the n plus 1 power. Then times, now take the denominator and invert and multiply, change it into a multiplication problem. So in the top you'll have n times 7 to the n divided by x minus 5 to the n. And again, the absolute value of that. So the whole thing is an absolute value. Now, just like in the previous videos, the idea is to cancel stuff out if you can. And the way to cancel most of these things out is to write them in an expanded form. So I'm going to rewrite this x minus 5 to the n plus 1 power. I'll write it as x minus 5 to the n power times x minus 5 to the first power. Because those two together is the same as this one, so I'll change that into that. Then down here, I'll do the following. I'll keep this as n plus 1. And I'm going to use the same trick here. I've got a 7 to the n here. I'd like to get a 7 to the n here. So I'll write this one as 7 to the n times 7 to the first power. Because remember, you add the exponents to get this. So I'll change this into this. And that's going to allow me to cancel some things out. So now that you've got it simplified, we'll again continue to work on down. And I'll write this as the limit as n approaches infinity. And again, I want to cancel out whatever I can cancel out. So what I've got is an x minus 5 to the n here and here. I can cancel these two out. I've got a 7 to the n here and a 7 to the n here. I can cancel those two out. And that will allow me to do the following. Again, here's my absolute value. And I've got, so in the numerator, what's left over? I've got an x minus 5 in the numerator. I've got an n in the numerator. I've got an n plus 1 in the denominator. And I've got a 7 in the denominator. So it looks like that. So we'll shorten this up just a little bit. And that takes care of the absolute value. So that's going to be equal to the limit as n approaches infinity. And I'll use the same little trick that I've used in the previous videos. If you haven't watched those previous videos, you might want to watch them because it explains this. If you've got a constant, I treat the x minus 5 as a constant. The variable in this limit is n. So you can treat the x minus 5 as a constant. Again, if you take the limit of a constant times something, you can bring the constant outside the limit. So what I'm going to do is bring this x minus 5 to the outside, and what that's going to leave me on the inside would be this. I'll just have an n in here. This is going to be an n plus 1 times 7. I'll close the absolute values, and I'm going to take this constant and move it to the outside, and I'll just assign it here with its own absolute value. I've got an x minus 5. Now, the only reason I do that is, to me, it makes it easier. When I'm working with just this limit, I like to have just the limit in terms of n and have all the x part on the outside. So now I'll go ahead and evaluate this limit. Now the next thing I'm going to do is distribute this 7. So that's going to become the limit as n approaches infinity of the absolute value. This again will be n divided by, this now becomes 7n plus 7. And then I've still got the absolute value of x minus 5 on the outside. Now again, you can think of this as being 1 here. And when you evaluate this limit, you might remember from your limit rules, if the power in the numerator is the same as the power in the denominator, if you take the limit as n goes to infinity, the limit just becomes the ratio of the leading coefficients. So it's going to turn into that. So this entire thing right here will just become 1/7. And then I've still got this absolute value of x minus 5. Now what that is going to be the limit. So I've showed that the limit is equal to this thing right here. And what the ratio test says is that the series converges whenever this is less than 1. So you can take this limit and check it to see, is it less than 1? For what values of x is it less than 1? I like to put a little question mark there just to remind me that that's what I'm testing. So now we will look at just this little piece right here. What this is going to be is I'm checking this, and the first thing I'm going to do, I've got 1/7 here, so I'll multiply both sides by 7, which will get me to this. This will get me the absolute value of x minus 5 is less than 7. Okay, now I want to solve this thing for the values of x. So whenever you have an absolute value, that means that you can rewrite it as x minus 5 is less than or greater than. Well, it's less than the positive value of this thing, and it's greater than the negative value of this thing. So that gets you to there. Now to solve for x, again on an inequality, I want to add 5 to each part. So I'll add 5 to this part, add 5 to this part, and add 5 to this part. And when I do that, that's going to give me a -2 here is less than, these will cancel out and give me an x is less than 12. Now what this is, this gives me an interval in which the thing is going to converge, but we need to draw a little picture of it here because we're not quite done yet. So if you actually just do a line to show what it looks like, it's going to look like this. So here is a number line, and I know from the beginning of the problem that it was centered at x is equal to 5. So somewhere in here I've got and I think I'll put it in black here, we've got an x is equal to 5. Then I know the right end point of this thing is going to be at 12, and it's going to be an open interval at this point at 12, and I know I go to a -2, and I've got another one over here at -2. Now, whenever you use the ratio test, at the completion of the ratio test, it will always be an open interval. You'll never have an inequality right here. But you're not quite done with the problem, because remember, the ratio test fails at the endpoints. So I'll put a little question mark right here. Maybe you include the endpoint right here, and maybe you include the endpoint right here, but you're not sure unless you test them. So at this point, you know that the radius of convergence goes from here to here. So the radius of convergence is going to be 7, and it goes this way, 7. But the only question now is what's going on with the endpoints. So again, we now drop down and go to step 2. The ratio test always fails at the endpoints, so you must test each endpoint separately using any appropriate test of the previous tests that you guys have had for determining convergence. So again, starting with the original problem, and let's go ahead and just rewrite the original thing. The original thing was, and this is going to be, we'll test the left endpoint first. So we'll test the left endpoint. So to test the left endpoint, take the left endpoint and plug it into the original series. So we had this summation from n equals 1 to infinity, and our original series was -1 to the n, and we had x minus 5, but we're going to go ahead and plug in a -2. So in place of x, plug in a -2 minus 5 to the n power. And then this is going to be divided by n, and this would be times 7n. So again, in place of x, you just plugged in a -2. Now you want to figure out whether this particular series converges or diverges. So that's equal to the summation from n equals 1 to infinity. And that's going to give you, in the numerator, you've got -1 to the n. And you can put these two together and get, so -2 minus 5 would give you a -7 to the n divided by n times 7 to the n. And that's going to be equal to the summation as n goes from 1 to infinity. And just a little algebra trick here. I've got a 7 to the n in the denominator, and I've got a -7 to the n in the numerator. So what I'm going to do is this. First of all, here's this -1 to the n. And out of this one, I'm going to factor out a -1 to the n times 7 to the n. So I can make that be, and change it to a positive, and move that negative out in front. And what that gives me, in the denominator, I've got this times 7 to the n. Now, the reason you want to do that is because now you can cancel out this 7 to the n. So this 7 to the n here will cancel out this 7 to the n here, and you're left with this. But what that's going to be equal to this summation from n equals 1 to infinity. Now notice, minus 1 to the n, these two are exactly the same. If one of them is negative, the other one's negative. They can only be a 1. So either they're both going to be a negative 1 or they're both going to be a positive 1. But in any event, when you multiply them together, you're going to get a positive 1 over n. So this entire series simplifies down to this. Now the question is, does this series converge or diverge? And again, a couple ways you can do this. Hopefully, if you recognize that, that's like having 1 plus 1/2 plus 1/3. It's a harmonic series. So that's the form of the harmonic series. And hopefully you know from your previous work that a harmonic series diverges. And you can also think of this as a p-series with the exponent equal to 1. So you're going to be able to show that this series diverges, and you can justify that with either the fact that it's a harmonic series, because you know that the harmonic series diverges, or you can think of it as a p-series with the exponent equal to 1. So either one of those two tests will show you that this thing diverges. Now again, if it diverges at the left endpoint, that means that you do not include the endpoint. So do not include the endpoint. So at this one, this is going to remain an open interval down here. So now what's going on at the right endpoint? So to test the right endpoint, so we'll test that. So the endpoint. And all you do is this time plug the right endpoint, plug a 12 into the original series. So that's going to be the summation from n equals 1 to infinity of minus 1 to the n. And again, in place of x, put a 12. So this is going to be 12 minus 5 to the n divided by n times 7 to the n. And that's going to give you the summation as n goes from 0 to infinity. Again, in the numerator, you've got still the minus 1 to the n. But this time, 12 minus 5, that's going to give you 7 to the n, divided by n times 7 to the n. Now, up here you had a negative 7 to the n power, and you had to factor something out. This time you don't even have to factor anything out. So in this case, just this 7 to the n here will cancel out this 7 to the n here. And that's going to leave you with this. Summation from n equals 0 to infinity of, in the numerator, you'll have a minus 1 to the n over n. And I like to write that in this form, right as the summation from n equals 0 to infinity. I like to put the minus 1 to the n over here, and then times 1 over n. Now again, hopefully you'll recognize what this is. If you wrote out the first few terms, this is actually going to turn into an alternating harmonic series. So when n is equal to 0, you would have 1. When n is equal to 1, you would have minus 1/2. Then you'll have a plus 1/3, a minus 1/4, and so on. So you can recognize that as an alternating harmonic series. Now again, to figure out whether it converges or diverges, you got a couple of choices here. You could also, one of the things you could use is the alternating series test. If you use the alternating series test, again, it says that it has two requirements. First of all, that each term has to be smaller than the preceding term, which is true. And also, the limit as you go off to infinity has to be approaching 0. And this series satisfies both of those, so you can use the alternating series test to show that this thing converges. And it converges by the alternating series test. And also, the fact that it's an alternating harmonic series converges. So you could use either one of those to show that it converges. And the fact that it converges tells you that you do include the endpoints. So I'll include the endpoints on this. Endpoints. So you don't include the left endpoint, and you do include the right endpoint. So again, test each endpoint separately. So again, back up here as far as how that affects the final answer would look like this. Now when we tested the left endpoint, it diverged, which means you keep this one open. When you tested the right endpoint, it converged, which means that you now change this from an open parentheses into a closed bracket. And the effect that it has on this is the final answer would look like this. It does not include the left endpoint, but it does include the right endpoint. So the final interval convergence is going to be that right there. So the idea is use the ratio test to find out where the endpoints are, which will give you the radius and the interval of convergence. And then you have to test each endpoint separately to find out whether you either include the endpoint or not include the endpoint. And when you test those, is just to test the left endpoint, plug in the left in, test the right one, plug the right one in. And again, if the series diverges, then you don't include it. If it converges, then you do include it. And as far as which test to use, just use whichever test fits the series that you're looking at. So there's another example using interval convergence.